Hi everyone, this is Gwen from EveCount Quantum Systems. Welcome to chapter 2 of our workshop. So, we're talking about the quantum engine. We, in chapter 1, established the what and the why. Now we're going to build the engine that powers the entire field. This chapter is about the fundamental laws of quantum mechanics, and it's not just theory, it's actually law. So, every algorithm, every experimental result, and every quantum device you will ever discuss is built on four unwavering rules. If you master these four postulates, you own the math, and they define the three key moments in any quantum system's life: its existence, its evolution, and its collapse. So, let's talk about the four rules, or the postulates 1 to 4. We begin by formalizing our reality. These aren't just arbitrary rules. They are the bedrock of our field. First, the state. A quantum system lives in what we call a Hilbert state. And it's not like a circle. It's actually kind of wibbly wobbly, timey wimey. And it's described by a unit vector. Why? Because the sum of all probabilities must equal 100%. If that vector isn't unit length, your probability fails. Second, the evolution. So this is your gate constraint. Evolution is actually unitary, meaning it is perfectly reversible. So if you run a quantum computer, you are simply applying unitary matrices. Then third, the measurement. This is the collapse. The moment you measure, the continuous vector of possibility becomes a single classical answer. It is the jarring point of dissonance between the quantum and classical worlds. Fourth, the composite systems. We use the tensor product to combine systems, and this is the source of the exponential power we talked about in chapter 1. So if you add systems, the space doesn't just grow, it actually expands exponentially or explodes. So now that we know the rules, we need the tools to act on them. How do we actually manipulate these vectors? We learn about something called the Pauli operators, X, Y, and Z. And this is kind of the famous graphic which has the circle and the three arrows, right? So think of these as your fundamental one qubit vocabulary. The X gate is your NOT gate. The Z gate flips the phase. When engineers build quantum hardware, they are essentially trying to replicate these three matrices using physical pulses. To visualize this, we use the Bloch Sphere. And in our map, cat 0 is the north pole, cat 1 the south, and every point on the surface is a potential quantum state. When we perform machine learning or feature engineering, we aren't just flipping bits, we're actually rotating this vector in 3D space. So how do we combine these? We use the tensor products. So this is the algebra of scaling. If qubit 1 has an operation A and qubit 2 has operation B, the total system operation is simply A tensor B. So when we want to perform operations in just one unit, we use the identity matrix, our do nothing operator, and this leads us to the two qubit gate, the C naught. And it's the first gate that introduces dependency. It checks the control bit and decides whether to flip the target, and it's the pivot point for entanglement. So I highly encourage you guys to actually do some research on how classical time series dependency can actually go all the way into quantum computation and information theory. Um, so let's take a look at the measurement projectors, right? The how do we know what is being measured, right? um, we use projector operators to mathematically describe the act of observation. So a projector, and you're talking maybe photonic system, it shines a light on a specific part of the Hilbert space, or a focus. And if you measure one part of an entangled system, very much like how you can even selectively lasso, you aren't just measuring that qubit, you're forcing a collapse on the entire the composite system. So this is why quantum information is actually so fragile and so powerful. Yeah, the moment of observation, that's when everything collapses. So we've built our quantum toolkit. We have the state, which is the vector, the gate, unitary, the measurement, which is the projector, and the system, the tensor product. Every complex algorithm you will learn in the coming chapters is just a different combination of these primary four rules. We have our foundation, so now in chapter 3, we ask, How do we build all possible computations with just a few simple gates?